The good news here is we're done with all the heavy computational stuff. Now we're just going to make some sketches, which will be a little refreshing. This is a really important skill to have. This is going to be tested majorly throughout the course. They're going to give you a graph, or I'm going to give you a graph of f of x, and we're going to want you to sketch the derivative. And the most important thing that I look for when I do or when I grade a problem like this is I look at the maxes and the mins of the original graph. I look right here and I see a slope of 0. Same thing here, I see a slope of 0. Oh, did I say slope? I certainly did. Isn't slope synonymous with the derivative? Yeah. All right, so right here, if the slope is 0, I need to come down on this dotted line and make sure that my graph, which is going to end up being in green, is at 0. Same thing here. All right. Now I'm going to get rid of the evidence, and I'll go to some other point on the graph. Let's say right here. Right here, to me, that looks like the slope is, well, it's definitely negative. It's going down and to the right, probably about -2 or so. I purposely did not put a scale on this just so you could have some freedom, but let's say -2 is down here. Okay, that's where I would be. Let's try somewhere else. Right about here, I think you can see that the slope to me there looks like maybe +1 or probably more like +2. So up along this dotted line, right from that point, I'll go to +2. That's where I'm going to be. Same thing, if I'm right about here, to me that also looks like it's about +2 or so. So it's about where I'm at. So right about there. And if you make enough of these dots and you connect them, I hope you can see what we're getting is a parabola. Let's make the dots a little bigger if you need to. A little artistic tip I can give. It's about the only artistic tip you're going to get from me. Look at that. And that is the graph of f prime. Cool. All right, we're going to pick up some steam now. Let's grab a couple of these dotted lines and just sort of bring them over. It's kind of fun. That's the only reason I do it. Yeah, it looks good. Maybe one right here and another right here. Okay, there's sort of random places. Okay, think about this. What if you were right here on this first dot? What would the slope be there? And I'm thinking it looks like +2. All right, and it probably is right around +2. So what you do when you're doing the derivative, which I'll make green, is you just go up to +2 along that line and just let yourself go. Now, I purposely didn't make markings on the y-axis just so you'd have a little freedom of expression. If you want to do that, that's fine. What about right here? What's the slope of the tan line there? I'm thinking, well, that looks more like 1. So go to +1. So that's right about there. And finally, for the last two locations, if you look at those blue tangent line slopes, they're very flat. I would say that this next one looks like it's probably a half, maybe a third. It's going to be around there or so. And finally, if you look at this one, f of x is still rising, but just barely. That slope is almost 0. So you go down right to about here. And I think you can see what is happening. F prime of x is this. And it will never go all the way down to quadrant 4. It's going to never touch the x-axis. The x-axis is a horizontal asymptote. So that is your derivative. And if you want to take it farther to the left, it really does go sky high. Because if you think about it, this is getting really steep. This red's getting steep down here. The slope right here, my gosh, you're probably going up 15 and over 1. And so by the time you would go along the dotted line, you'd be way up here somewhere, probably off the graph. So yeah, that's it. Now, a good question that students ask is, how accurate do you need me to be? Or how accurate will College Board expect me to be? And that's a great It's a great point. Here's what they will do. A lot of times I'll see this in multiple choice format. They'll give you the red graph. They'll say, here's f of x, and then they'll give you 4 answer graphs, and they'll say, which of the following could be the graph of f prime, or the derivative? And let's say the correct answer is C. They make it look like ours. And then B, they do something stupid that's wiggly. Maybe A is a straight line, and D is a curve going the wrong way. So you don't have to be, Pablo Picasso to get it right, but you have to be reasonably close. And I want you to make a sketch, but it should be a reasonably accurate sketch. If I see you going below the x-axis, that's an issue. Or if you're going the wrong way, obviously I can't turn a blind eye to that, but that's my expectation. Sketch it, but try to be as neat as you can. Let's put some markers down. About 1 there, 1 there. I'd like to put 1 in the middle, but I don't think you could see it because of the axis. I'll off-center it slightly, but that's meant to be right at the y-axis. All right, at this green dot, what's the slope of the red graph? And I would say it's 1, positive 1. So I'll go with the positive 1. Maybe it's right about there. What's the slope over here? That green dot. Well, I would say that's negative 1. So let's go down to negative 1. That looks about right. In fact, here's what's weird. It doesn't matter where you are along this part of the line. The slope is positive 1 the whole way, which means the derivative is going to be positive 1 the whole way. And same thing if you're along this anywhere, not just this location that was at before, but any of those, the slope's going to be negative 1 the entire time. So the derivative is going to be down there. So the question is, what happens here when you get to the y-axis, when x is 0? What's the slope right there? And the slope cannot be 1 and negative 1 simultaneously. It's impossible. You have to pick one. You don't want to pick favorites. That's like a teacher picking favorites. That's not cool. So which one is it? And the answer is neither. So you have to have an open circle right there. If you filled in both circles, 2 bad things would happen. You'd be claiming that the slope is 2 separate numbers at the same time, which is impossible. You'd also be violating the vertical line test. And so f prime of x, which is supposed to be a function, would not be. All right. Now, a lot of people are like, what about 0? I mean, isn't this point right here a maximum? I'm like, yes, it is a max. Well, didn't you say that, that means the derivative would be 0? Yes, if it had a derivative there, but it does not. And we'll talk about that in a moment. Who's to say the slope there is 0? I mean, this is a tan line. So is this. Those are all tan lines. They only hit the curve once, every single one of them. How do you know it's the 0 one? You don't. Okay, so the derivative's graph is the green. It is a function that has jump discontinuity at x equals 0. How about that? It's a function, but it's not a continuous function. And the issue was this sharp corner right here. Corners cause problems. In fact, corners are one of 4 different things that can cause problems. Here are those 4. The 4 situations that ruin what we call differentiability at a point. Differentiability literally is the ability to take a derivative. We already saw that corners are an issue. If you have a corner right there, you don't have a derivative. A cusp is similar to a corner. In fact, College Board doesn't make any differentiation between the 2 terms, so you can use them sort of, you call them all corners if you want. A cusp is a corner with a bit of attitude about it. As much as I wouldn't want to, scrape my arm or my finger along that, and pierce myself, I definitely don't want to get jabbed by that thing. That's even nastier. A cusp is when the slopes are heading towards infinity and negative infinity. Obviously, you can't have both in the same location. So, like I said, a cusp is a corner with a bit of a bite to it, a bit of attitude. Vertical tangents happen, like the arctan graph has this shape, so does the logistic curve from pre-calc. right here at this very moment, the slope is temporarily, for a nanosecond, undefined. Like the slope right here is probably positive a half. The slope right here, positive 1. Here the slope is close to 0. But right here, the slope's vertical. And a vertical tangent, if you don't have a slope, you can't have a derivative. In fact, that point right there has a name that we're going to learn later on in the class, and it's called a point of inflection. And finally, last but not least, discontinuity will ruin derivatives. Discontinuity, as we know, comes in 3 flavors: point, jump, and infinite. So I'll just pick one. Let's say jump discontinuity. Function's coming along, and suddenly you have this. Well, there's no derivative right here because of the discontinuity. And that should make sense that there's no derivative, because earlier in this section we defined the derivative to be the limit as h approaches. Oh wait, I said limit, didn't I? Yeah. Ooh, the limit right there doesn't exist. And if the limit doesn't exist, certainly the derivative won't exist, since the formula of derivatives have limits in them. So discontinuity is an issue. All right. There are also 2 statements buried in the book that are really important to understand what they truly mean. The first one's a little easier. It's differentiability implies continuity. The mathematical symbol for implies is a right-facing arrow. And implies really loosely translates to causes it to happen. So if you are differentiable, in other words, if we can take derivatives on you everywhere, well, that means or implies that you have to be continuous. Because if we can take derivatives, if you're differentiable, then none of these 4 things are happening. And if discontinuity can't happen, then you have to be continuous. Kind of makes sense. All right, so that one's out of the way. This is not true backwards. If you're continuous, it doesn't mean you're going to have derivatives. I mean, these first 2 examples, actually these first 3 examples, those were all continuous, but they didn't have derivatives for one reason or another. Corners, cusps, vertical tangents occurred. All right, but it's true left to right. If you have derivatives everywhere, you're continuous. The second one is a little less obvious. Differentiability implies local linearity. When I see local linearity, I see the word line peeking out. And when I see the word local, I think if somebody's a local, that means they're from Beechwood, or at least from Greater Cleveland, Northeast Ohio. If you meet somebody in another country and you're like, I'm from Beechwood, Ohio, and they're like, oh my gosh. Even if they're from Mentor or Willoughby or somewhere like that, they're practically your best friend, because you can relate to them. You ever been on Google Earth and you start to zoom in, you see the whole Earth, and you zoom in on the app and you're into North America, and then you're like, let's go to Ohio. You find Lake Erie and you zoom in on Greater Cleveland, and then Beechwood, you see 271 on the map, you can see Beechwood Mall, and you're like, oh, let's find my house. We've probably all done it. And you zoom in on your house and you can see cars in the driveway, and you're like, oh, that's creepy. Oh, we had that car like 3 years ago. This must be an old picture. Sure enough, that's about as local as you can get. The same thing is true here. Let's say that we took 2 functions. The first function here in green will behave itself and be a nice curve. And then the second function, not so much. It'll have a nasty cusp right in the middle of it. And let's say we decide to go local. We zoom in right here. Well, if you zoom in on a calculator, instead of seeing the whole thing, you'd see like this. But let's say we zoomed in more. We zoomed in like 100 times or 10,000 times. After a while, you wouldn't be able to tell it was a curve anymore. It'd be all pixelated. It would be a straight line. Yes, if things have derivatives, if they're differentiable, that causes you to see a line when you get super local, when you get super zoomed in. I don't care how many times you zoom in on this, you're still going to see the cusp unless you zoom in on the wrong place. And that's because, it has a derivative here and here, but it does not have a derivative there. You can zoom in 10,000 times and you're still going to see the cusp. All right? So that's what the second one means. If you have derivatives, you're going to look like a line anywhere I should decide to zoom in.